So quiz 8 starts off with question 1 here. It says you kick a 450-gram soccer ball towards a goal with an initial speed of 25 meters per second. Neglecting air resistance, how fast is the ball moving when it reaches 1 meter in height? And the hint here is that you can use conservation of energy for this question. Okay, so we need to think about the two states that we're going to analyze in this problem. There's the ball on the ground. So it has kinetic energy right after you kick it, and it has 0 potential energy. So I'm just going to draw a little bar graph to represent that. A few moments later, it is 1 meter off the ground over here. And it has some kinetic energy, but it's lost a little bit, and it's gained some potential energy. Okay. And this is a conservative force that we're dealing with, gravity, and there's no external work being done in between these two states. So we can use our conservation of energy laws, just like the hint tells us. So our initial energy, it's all kinetic, and it's just equal to 1/2 mv squared. Our final energy is equal to kinetic energy plus potential energy. That should be an F for final kinetic here. So that is 1/2 mv final squared plus mgh. And then to differentiate this v final from our v initial, I'll make sure I put a 0 here. V initial and v final. So we can plug in the numbers that we have to fill in most of the values in these two equations. We can set these two equal because we know that initial energy is equal to our final energy. So we're left with 1/2 mv0 squared is equal to 1/2 mv final squared plus mgh. So you can tell that we have an m in each term, so we can just cross the m's out. We know the initial velocity is 25 meters per second. To save space, I'm not going to write out all of the significant figures here. We're trying to find v final, so I'll leave that as vf. We know that g is 9.8 meters per second squared, and our h is also given, that's 1 meter in height. So I'll plug in some of these numbers to my calculator. 1/2 times 625 meters squared per second squared. 1/2 v final squared plus 9.8 meters squared per second squared. If I rearrange this a bit, multiply everything by 2, I'm going to cross out these 1/2s and put a 2 here. I end up with v final squared is equal to 625 minus 9.8 times 2, which is 19.6 meters squared per second squared. And I can put that into my calculator. 625 minus 19.6, 605.4. Meters squared per second squared. I take the square root of that. And I get that VF is equal to 24.4 0.6 meters per second. So if we move on to problem 2, it says a short time later, the ball, its mass is still 450 grams, reaches a speed of 24 meters per second in the x direction. What is its momentum in the x direction? So this is pretty straightforward. We're just going to use that p is equal to m times v. In this case, px is equal to m times vx because we've got everything contained in the x direction here. So the mass is still 0.450 kilograms. I'm going to keep everything in kilograms, meters, and seconds for SI units. And the speed in the x direction is 24.0 meters per second. So if I plug that in, then I end up with 10.8 kgms, kilogram meters per second. Okay, so we'll move on to problem 3 here. So at this point, the goalkeeper has leaped into the air to catch the ball. Considering the ball and the goalkeeper as one complete system, in what directions is linear momentum conserved? So here x refers to the horizontal direction, and y refers to the vertical direction. Neglect air resistance and consider Earth's gravity to be the only external force. So this is a qualitative problem rather than a mathematical problem. So we need to think about the conditions under which linear momentum are conserved. So momentum is conserved if and only if there's no external force. And these are both vector quantities, so we can break this down to say that momentum in the x direction is conserved if there is no net external force in the x direction, and so on for the y direction, z direction, whatever direction you're interested in for your problem. So, in our case, we have the soccer ball, and it's moving to collide with our goalkeeper here. Soccer ball is 1, the goalkeeper is 2. In this case, the goalkeeper has already left the ground. The ball has already left the ground, so there are no forces acting in the x direction. The only forces here are gravity, so both of these masses have a weight pointing down. So from our perspective, there's a net external force in the y direction, so momentum is conserved only in the x direction. Py is not conserved. So let's take a look at the next problem here. It says that the goalkeeper manages to catch the ball, and just before the catch, the keeper is in midair and has 0 velocity in the x direction. What is the total momentum in the x direction of the goalkeeper holding the soccer ball after making the catch? So we have here a simplified soccer ball and the goalkeeper. The soccer ball has some initial velocity, which we know from the previous problems, and we're given that the goalkeeper has no velocity in the x direction. Afterwards, they're stuck together, and we can treat them as one mass, which we'll call capital M. Capital M is equal to the mass of the soccer ball plus the mass of the goalkeeper. So what's the momentum of our initial system? Well, the goalkeeper isn't moving, so the goalkeeper contributes no momentum. So all the momentum is coming from the soccer ball. But we've already calculated that in the previous problem. So we know that our initial momentum is equal to 10.8 kgms. And we know from our previous problem also that momentum is conserved in the x direction, so p0 is equal to p final. So just by writing this down, we've already solved the problem. We know that p final is equal to 10.8 kgms. The question's only asking the total momentum in the x direction. But let's suppose that the problem was asking us to go one step further and find the velocity of the goalkeeper in the x direction. So if we want to do that, we need to break things down a little bit further. We need to write down the momentum of the combined goalkeeper and ball in the final picture. So we're still going to use our P equals mv equation, but here the mass is capital M, and we're dealing with V final. So capital M, it's just 80 kilograms plus 450 grams. And V final is our unknown. So I'll put 10.8 over here on the left side. So V final will turn out to be 10.8 over 80 plus 0.450. And our final units are meters per second. So if I plug that in, I get 0.13 meters per second. So again, let's check the signs and make sure everything makes sense physically. We've got a motionless goalkeeper. We've got a positive velocity ball moving to the right. So our right is our plus direction. Left is negative. So we have a positive momentum. The momentum in this case is moving to the right. Positive momentum over here. We expect the goalkeeper will be knocked back in the direction that the ball is going, which is positive. So our V final is positive, and this all checks out, and this all makes sense. So the last question says, after the catch, the goalkeeper lands flat on the ground, moving downwards at 4 meters per second at the time of impact. The grass cushions the fall, and the keeper comes to a stop 0.1 seconds later. What is the net force experienced by the goalkeeper upon hitting the ground? And the question says that we can neglect the mass of the soccer ball in this question. Okay, so we've got our grass here. The goalkeeper hits the ground and is moving downwards at 4 meters per second. And a few moments later, hits the ground and stops at 0 meters per second. And this all happens within a span of delta t equals 0.1 seconds. So to solve this, we're going to use our restatement of Newton's laws. So we initially learned this as net force is equal to m times a, but we also learned another way to write this is the change in momentum divided by the duration of time, or delta p over delta t. So we also know that as long as mass remains constant, delta p can be written as m times delta v. So our goalkeeper isn't gaining or losing any weight during this. So this holds true, and we can use m delta v as our delta p here. And then delta t is given to us in the problem. We're told that this all takes 0.1 seconds to happen. So we'll plug in our numbers here. The mass, 80 kilograms. Delta v we can write as v final minus v initial. So our final is 0 and our initial is 4. So let's write this as 0 minus 4 meters per second. And all divided by 0.1 seconds. So all we need to do now is just plug these numbers into our calculator, and we end up with negative 3,200 newtons. And we know that we can use newtons here because we kept all of our units here, kilograms, meters, seconds, using our standard SI units. Okay, so the average force experienced is 3,200 newtons. So why is the force negative here? Well, we made this a positive number. So in this case, we've sort of defined the positive direction as going downward. If we wanted to make all the signs come out right, the way that we normally like to have them, we could define positive as pointing upward. In which case, this will need to be a negative 4 meters per second. And this equation here would be 0 minus a negative 4 meters per second, or just plus positive 4 meters per second, and our force would come out positive.